This is part 6 of a series on generative adversarial networks. In this video, we will look at least squares GAN, shortly LSGAN. This video was produced in Korean and translated into English. My voice is generated by AI, text-to-speech. In this video, we will look at LSGAN, one of the GAN variants that improves the instability of standard GAN. LSGAN was introduced in 2016 by Xudong Mao et al. In their paper, Least Squares Generative Adversarial Networks. Let's read the abstract of the paper. Regular GANs hypothesize the discriminator as a classifier with the sigmoid cross-entropy loss function. However, we found that this loss function may lead to the vanishing gradients problem during the learning process. To overcome such a problem, we propose in this paper the Least Squares Generative Adversarial Networks, LSGANs, which adopt the least squares loss function for the discriminator. We show that minimizing the objective function of LSGAN yields minimizing the Pearson chi-square divergence. Minimizing the objective function of regular GAN yields minimizing the Jensen-Shannon divergence, as we saw in the first video of this series. There are two benefits of LSGANs over regular GANs. First, LSGANs are able to generate higher quality images than regular GANs. Second, LSGANs perform more stable during the learning process. We evaluate LSGANs on 5 scene datasets, and the experimental results show that the images generated by LSGANs are of better quality than the ones generated by regular GANs. Let's look at the difference between sigmoid cross-entropy loss and least squares loss. The discriminator acts as a classifier that distinguishes between real data and fake data. If real data and fake data are distributed like this, the discriminator will create a decision boundary like this. All data points to the right of this boundary will be classified as real data, and all data points to the left will be classified as fake data. That is, d of x is 1, and d of g is 0. If the fake data gets a little closer to the real data, the decision boundary will probably look like this. Then d of x will decrease, and d of g will increase. For example, d of x might decrease to 0.7, and d of g of z might increase to 0.3. If the fake data and the real data are very similar like this, then both d of x and d of gz will be 0.5. Figure 1, presented in this paper, illustrates this situation. The blue cross data points are fake samples, g of z, generated by the generator. And the red circle data points are real samples, x. This is the decision boundary of the sigmoid cross-entropy loss function. Note that the decision boundary should go across the real data distribution for a successful GANs learning. Let's assume that all data points to the right of this boundary are classified as real data, and all data points to the left are classified as fake data. And let's take a look at the data points around here that were generated by the generator. These are far from the boundary, but to the right of the boundary, so they are classified as real data. That is, their binary cross-entropy loss is a very small value, close to 0. This type of loss is the hinge loss shown in Figure 2 of the paper. We took a closer look at hinge loss in the third video of the Support Vector Machine series. This is the decision boundary. Misclassified samples have larger loss the further they are from the boundary, while correctly classified samples have loss close to 0, no matter how far they are from the boundary. These samples have very little loss, but are far from the real data. Since the loss is small, the gradient of the loss vanishes, and the generator is not updated. Since the discriminator believes that these samples come from real data, the generator keeps trying to generate these data points that are far from real data. This is the problem with regular GANs that the authors of the paper pointed out. To solve this problem, the authors of the paper proposed LSGANs, which adopt the least squares loss function for the discriminator. This figure shows the decision boundary of the least squares loss function. In this case, the decision boundary also goes across the real data distribution. The decision boundary does not have to be like this, and it could be like this, or it could be like this, depending on the configuration of the discriminator model. In this case, we assume that the bottom of the boundary is the correct side. The least squares loss function looks like this. This is the decision boundary. The further a data point is from the boundary, the greater the loss, regardless of whether it is correctly or incorrectly classified. That is, using the least squares loss function increases the loss for these samples. The least squares loss function will then penalize these samples and pull them toward the decision boundary, even though they are correctly classified. Based on this property, LSGANs are able to generate samples that are closer to real data. Now let's look at the loss function of LSGAN. Let's first look at the loss function of a regular GAN. The loss function of the discriminator of a regular GAN is as follows. Next, let's look at the binary cross-entropy for a single data point. The output y-hat of the discriminator for a data point x from the real data is d of x, and the target y is 1. Then the binary cross-entropy loss for x can be written as follows. Since y is 1, this can be simply written as follows. The output of the generator for random noise z is g of z. The output y-hat of the discriminator for g of z is d of g of z. And the target y is 0. Then the binary cross-entropy loss for g of z can be written as follows. Since y is 0, this can be simply written as follows. The objective of discriminator is to classify real samples and fake samples. This can be achieved by minimizing the binary cross-entropy. Alternatively, it can be achieved by maximizing the negative binary cross-entropy. In this way, we can see that the loss function of a regular GAN is derived from binary cross-entropy. Next, let's look at the loss function of LSGAN. As seen on the left, when viewing the discriminator as a classifier, regular GANs adopt the sigmoid cross-entropy loss function. As mentioned in the previous page, when updating the generator, this loss function will cause the problem of vanishing gradients for the samples that are on the correct side of the decision boundary but are still far from the real data. To remedy this problem, the authors of the paper proposed LSGANs. Suppose we use the A-B coding scheme for the discriminator, where A and B are the labels for fake data and real data, respectively. Then the objective functions for LSGANs can be defined as follows, where C denotes the value that G wants D to believe for fake data. For D, it is minimum when each term is 0, so it's minimum when D of X becomes B, and D of GZ becomes A. And for G, it is minimum when D of GZ becomes C. For example, we can use the following values for A, B, and C. We will look at this in more detail on the next page. The benefits of LSGANs can be derived from two aspects. First, unlike regular GANs, which cause almost no loss for samples that lie in a long way on the correct side of the decision boundary, LSGANs will penalize those samples even though they are correctly classified. When we update the generator, the parameters of the discriminator are fixed, i.e., the decision boundary is fixed. As a result, the penalization will make the generator to generate samples toward the decision boundary. On the other hand, the decision boundary should go across the manifold of real data for a successful GANs learning. Otherwise, the learning process will be saturated. Thus, moving the generated samples toward the decision boundary leads to making them be closer to the manifold of real data. Second, penalizing the samples lying a long way to the decision boundary can generate more gradients when updating the generator, which in turn relieves the problem of vanishing gradients. This allows LSGANs to perform more stable during the learning process. This benefit can also be derived from another perspective. As shown in Figure 2, the least squares loss function is flat only at one point, while the sigmoid cross-entropy loss function will saturate when X is relatively large. Next, let's analyze the loss function mathematically in more detail. As we saw in the first video in this series, in the original GAN paper, the authors has shown that minimizing the loss function yields minimizing the Jensen-Shannon divergence. Here we also explore the relation between LSGANs and F-divergence. Consider the following extension of the loss function of LSN, shown on the previous page. Note that adding this term to V of G does not change the optimal values since this term does not contain parameters of G. We first derive the optimal discriminator D for a fixed G as below. Using the integral symbol, we express the expectation as follows. We looked at why the second term can be written this way in the first video of this series. Fixing G, and partially differentiating this part with respect to D of X, we get the following expression. Then the optimal discriminator D is as follows. To simplify notation, let D be P data and G be PG. Next, we substitute D star into the function V of G to find the optimal G. Then, this equation can be written as follows. The optimal V of G is denoted as C of G. And rearranging this equation gives us the following expressions. If we set b minus c to 1 and b minus a to 2, this expression can be written as follows, where this is the Pearson chi-square divergence between d plus g and 2g. Since d is p data and g is pg, this equation can be written as follows. Thus, minimizing these equations yields minimizing the Pearson chi-square divergence between p data plus pg and 2pg. If a, b, and c satisfy the conditions that b minus c is 1 and b minus a is 2. If p data and pg are equal, the chi-square divergence is 0. We can see that the regular GAN minimizes JSD, while the LSGAN minimizes chi-square divergence. One way to determine the values of a, b, and c is to set a to -1, b to 1, and c to 0. Then a, b, and c satisfy these conditions. We then get the following objective functions. Another method is to make G generate samples as real as possible by setting C equal to B. For example, by using the 0 and 1 binary coding scheme, we get the following objective functions. V of D is minimum when D of X is 1 and D of GZ is 0. And V of G is minimum when D of GZ is 1. The paper notes that in practice, these two cases show similar performance. Thus, either one can be selected. So far, we have looked at the basic architecture of LSGAN and analyzed the loss function. In the next video, we will implement a LSGAN and a LSDC GAN to see if they improve the mode collapse phenomenon.